Only this time, we're going to look at the difference of two proportions in our sampling distribution. Essentially, we're taking two sampling distributions and combining them into one, looking at how that works. Okay? So, that's what we're doing today. It shouldn't be that bad, but the process is kind of tedious, I guess. I think once I'm not leading you through it, you'll be able to knock out the procedure pretty quick, though. That's what I'm hoping. Let's see. Your asynchronous, lesson 7.3. That is on the website. That is a Teams assignment, I do believe. And then your next homework assignment is also up online. Maybe I should put that in there. I don't know how often I'm going to need to remind you of this, but I think that's always going to be on the online textbook, but I'll keep writing it for now. Let's see. Oh, so I have an idea for changing the homework grading for that online textbook. So I'm going to try it for the next assignment or two, see how it works. So now on those online problems, you get 2 attempts. All right, you only get 2 tries for each problem. 2 tries. And then I think I had it, you lose 20% for each try that you do. I want to see how that goes. Now, I like the idea still, though. If you get 70% overall, I'll still give you full credit. So that's still in effect. But this way, you can actually miss some points if you get things wrong too often. Gonna try that, see how that goes. Because otherwise, it still would have been possible to just guess on every single problem, every single answer choice, and still get 70%, which would give you credit. So I want to try this. So each question, you get 2 attempts, minus 20% for each attempt. I don't know, we'll see. We'll see. Pretty much when I was looking at the report, pretty much everybody was getting like 90% or so on the homework. So should all be good there. Should all be good. I got the first one in for 3rd period. So that is now an atlas. You either have, I think you pretty much either have the 100% or you have a 0%, whether you did it or not. So, alrighty, picture of the day today. You ready for this? You ready for this? Nothing too exciting, but it's just me bragging. Again, it's all about entertaining myself, right? Am I on the wrong monitor? I am on the wrong monitor. Primary. There we go. There we go. So this is where my progress is for my son's bed frame. So that's what it's looking like right now. I think it's coming out pretty nice. It's huge. It's barely gonna fit in his room, but I think it will fit. But he's got the bunk. He's got the slide. It'll give him lots of space underneath to play. It's coming along. It's still fall. I don't think I'm going to get it done by his birthday. His birthday is January 31st. I don't know if I'm going to get it done in time. Started woodworking. Yeah, it's one of those things where if I had to do it every day, all day, would I still like it? Bob the Builder. Give me a break. Bob. I'll take that as a compliment. It's still far from done because once I get all assembled, I have a little bit more assembly stuff to do. Then I got to take it all apart, sand it for days. Sanding is like 90% of woodworking, by the way, is sanding. I got to sand over all the edges, and then I've got to put a clear coat over it to protect the wood and to make sure that over time splinters don't start coming off and, getting on him when he slides down. So that's going to take quite a while. But I'm looking forward to getting that in his room at some point. It's fun stuff. Alrighty, ladies and gents. You got some paper out. You got a pencil out? You ready to do this? Sampling distributions for the difference of two proportions. All right, now, to start out, however, I do have a quick pop quiz for you. All right, I want to see how you're getting the other stuff that we're doing, that we've done so far. So this pop quiz is in Teams, okay? So everybody head on over to Teams. I know we're all sort of in Teams right now, but go to your assignments. There should be a quiz there waiting for you. I'm going to give you about 15 minutes, I think, to try that out. It's only 4 questions. 15 minutes might be a bit long. It's 4 questions. It's all the same scenario, but it's like an A, B, C, D. Okay. Head on over to the Teams quiz there. It should show up underneath assignments. It's for sampling distributions of proportions. Pop quiz, it says there. It's also in the general channel. You can just click right there. Should take you to it. But give you about 10-15 minutes there to try that out. I want to see how we're doing. As we are getting close to the end of this unit, actually, surprising. Our test will be next week, Thursday, for you all. Next week, Thursday, is our first exam. It's a quick unit, but most of the units this semester are going to be quick. Most of them are like 3-4 weeks. We don't have any big 5-week units like we. I'm moving on here. Hit submit there. Get those in, please. All right. We are moving on to new stuff here. You ready? New stuff. I say new stuff loosely, actually, because almost everything from here on out in this unit, we've kind of done already in one way, shape, or form. And so I'm hoping it's smooth sailing to the end here. There isn't a whole lot of new stuff. I think you've done the hard new things. Now, that's not going to still be not difficult or complicated, but we have mentioned and talked about most of these concepts already, especially everything after this one unit. Nothing bold. I don't know about this difference of proportions nonsense. Hopefully I can prove that we have kind of done a lot of that. So, we did do some of this way back in chapter 6 when we were combining random variables. All right. When we combine random variables, you take like a normal model and you combine them into one. What happens when you do that? What happens to the shape, the center, and the spread when you combine 2 random variables? And so here are the big ideas that we learned about what happens when you combine random variables, which is the same thing that happens when you combine sampling distributions, when you subtract or combine the proportions. Okay, so the shape, a normal distribution plus or minus a normal distribution is a, normal distribution. Why is my, wow, right when I start using my number pad thing, it dies? That's awesome. Where are we here? No, not you. All right, this is the right cord. Hopefully this gives me power. Hey, there we go. All right, is a normal distribution. There we go. All right, the center. If you take a normal distribution plus a normal distribution or minus, you can simply add and subtract the middle, the mean. All right, now the weird one was when you're combining random variables for all this is the spread. You cannot add or subtract the standard deviation. All right, you can combine the means, you can combine the centers, but you can't combine the standard deviations. The way we figure out the new standard deviation is that you can add the variance. You can add the variances together, and you always add. Even if you were doing a normal distribution minus a normal distribution, it still becomes more variable. The spread still increases, so you always add the variances no matter what. And then if you want the standard deviation, you go ahead and you square root, and to go back to a standard deviation. But if you're combining the variables, you can only add the variances. Maybe that sounds a little bit familiar. All right, so why the heck would we ever do this? Bolt, I'm still lost. I need some context, all right? Why would you do this? So here's a scenario that can hopefully show you why you might want to combine proportions. All right, so scenario. Suppose there are two large high schools, Edison and Sunnyside. At Edison, 70% of the students did their homework over the weekend. At Sunnyside, only 50% of the students did their homework over the weekend. Bolt takes an SRS of 100 students at Edison and records the proportion, P1 hat, of students who did their homework. Mr. Schneider at Sunnyside, he's the AP Stats guy at Sunnyside, takes an SRS of 200. I guess Bolt's lazy, huh? Takes an SRS of 200 and records the proportion, P2 hat, of students who did their homework. So Edison's P1, Sunnyside's P2. To compare the results, we will take P1 hat minus P2 hat and make a sampling distribution. All right, so we want to compare the proportion of students who did their homework at Edison and Sunnyside. To do that, we're going to subtract the proportions. All right, so if this result is positive, that means Edison did more homework. If this result was negative, that means a higher percentage of Sunnyside students did their homework. Now, first off, we've got to treat these two things separately, okay? If we're going to combine them, we have to check the mean, standard deviation, all our conditions for both of them. So, what is the shape of Edison's sampling distribution? Well, we hope it's normal, right? But to do that, we have to do n times p and n times q, and they both have to be greater than 10, right? So let's do that. So the sample size that I took at Edison, because I'm lazy, was 100, times the proportion. The proportion for Edison was 70%, 0.70. That's nice and easy. That is 70, greater than 10. 100 times Q, well, that would be 30%, right? So that would be 30. Also greater than 10, check. So our shape is, in fact, normal. All right. The center, what is the center of the distribution here? Well, the mean of all the P1 hats for this sampling distribution is just the 70%, the population proportion. All right, and the spread, the standard deviation of P1 hat. Whew. That syntax gets pretty brutal. Subscript of a subscript with a superscript. It's good stuff. Why is it normal? Can we? Yeah, so it's normal because the sample size is big enough. If you remember, we did our the graphic organizer last time, where even if the population is skewed left, if your samples are big enough, then the sampling distribution will still be normal. Okay, if you take samples that are big enough. And how do we know it's big enough? Is if n times p is greater than 10 and n times q is greater than 10. That's when you know the sample size is big enough. For sure, for sure. All right, the spread. So our standard deviation here is the square root of p times q, so 0.70 times 0.30 divided by our sample size, which is 100. Type that into your calculator. We get 0.7 times 0.3 divided by 100. Square root that answer, and we get 0.0458. Now, again, we make our nod here that we are assuming that we are sampling less than 10% of Edison. We are assuming that our SRS of 100 is less than 10% of the population of Edison, which that is a perfectly good assumption. Edison is much larger than 1,000 students. All right, so there's our first sampling distribution. Now we got to do that for Sunnyside as well to make sure it meets all of our conditions. All right, so first, shape. Is our shape normal? We got to test n times p and n times q. So n times p, they had 200. Schneider's not lazy like I am. Times p, his proportion is 50%. Did their homework. Also be easy for us, right? And then 200 times how many did not do their homework? Well, it's got to be 50%. Both of those are definitely bigger than 10. So yes, we are normal. Take away that question mark. The center, what is the mean of P2 hat? The mean there is 50%, right? The same proportion as the population. And his standard deviation of P2 hat is equal to the square root of 0.50 times 0.50 over his sample size, which was 200. Where'd my calculator? There we are. So 0.5 times 0.5 divided by 200 square root is 0.035. Again, I suppose we should say that we are assuming that our SRS of 200 is less than 10% of the population of Sunnyside. Ooh, that one might be a little dangerous. I think Sunnyside's over 2,000, isn't it? Sunnyside's big. Yeah, Sunnyside's big. Definitely over 2,000. So, a little closer there, but we'll assume that, yeah, Sunnyside is over 2,000 students. I think that's still pretty safe. All right, so what we're going to do now is we're going to take these two normally distributed sampling distributions. We want to be able to compare them, so we're going to subtract P1 hat minus P2 hat, okay? So our combined sampling distribution here is going to be P1 hat minus P2 hat. So first, what is the shape? Well, if I take a normal distribution and I subtract a normal distribution, the shape will again be a normal distribution. So if you're ever asked, hey, what's the shape of this combined sampling distribution? You have to check n times p, n times q of the first one, and n times p and n times q of the second one. If both of those are normal, then the combination is normal. All right, what is the average, the center of P1 hat minus P2 hat? What is the center of this sampling distribution? Well, it's going to be 0.70 minus 0.50. So the center of this sampling distribution should be 0.20. You can simply subtract the means. All right, what is the standard deviation of P1 hat minus P2 hat? All right, now this one is where it takes some calculation, okay? Because we can't simply take the standard deviations and combine them. You cannot add or subtract standard deviations. You have to go back a step to the variance, then we can add the variances, okay? So the way we might write this, the variance of P1 hat minus P2 hat is equal to the variance of P1 hat plus the variance, it's variance because I have the squared there, of P2 hat. So I'm simply going to take this number over here, 0.0458, square it, plus 0.035 squared. So I'm squaring them to get the variance, then I'm allowed to add them. Where's my calculator? So 0.0458 squared plus 0.035 squared. Square root that number. Now, all right, I'll go step by step, my bad. 0.0332. So the variance is equal to 0.033. Ooh, 2 zeros, my bad. That's our variance, but we don't want the variance. We do want the standard deviation. So we then do square root all of that. So the square root of that number. 0.0576. 0.0576. That is our standard deviation. Whew. All right. That's a lot, but I'm hoping that process gets faster when I'm not explaining it the whole time, because it is basically the same procedure you just did in your quiz, right? The same procedure that you did in your homework. You just got to do it twice. You got to do it once for the first population, once for the second population. If they both check out, they're normal, you got this middle, you got the standard deviation, then you can combine them. Find your new middle and your new standard deviation. And then the fun begins. Bolt, I hate you right now. I know. It's cool. It's cool. All right, so now that we have our standard deviation and our mean, and we know it's normal, I can now ask you some analysis questions. Okay? So estimate the probability that P1 hat minus P2 hat is positive. What was the last step to finding? The last one was square root, Renato. So when we did this number right here, that was our variance. And so to go from variance to the standard deviation, we square root all of this. Square root, square root.
It's gonna be. It's gonna be.
It will be legendary, but not yet. All right, what do we got here? What do we got here? All right, so now I can ask you this probability question. What is the probability that P1 hat minus P2 hat is positive? This is just a normal CDF. Because now we have this normal sampling distribution. I can just ask you normal CDF questions about it. Perfectly normal. Okay? But because it's way over there, now I forgot the numbers. So I'm going to write them down. The mean of P1 hat minus P2 hat was 0.2, right? And the standard deviation of P, this is really annoying to write this every time, isn't it? It's a good thing your homework is multiple choice. Was 0.0576. There we go. So there's this sampling distribution. The middle is at 0.20. And then we have our standard deviations that go out, right? Etc., etc. I want to know the probability that this is positive. Okay, meaning positive numbers are bigger than 0. So 0's over here somewhere. I don't know where. Because 0.20 is the middle, so 0's over here. I want to know the probability that we're greater than 0. That is simply a normal CDF where the mean is equal to 0.20, the standard deviation is equal to 0.0576, and the lower is 0, and the upper, oh, well, it goes on forever, doesn't it? So you just need a really big number here, like 1,000. Plenty big enough in this case. That will give me the probability that P1 hat minus P2 hat is positive. Distribution, normal CDF, lower, 0, upper, 1,000, my mean, 0.20, my standard 0.0576. 99.97%. Woo! All right, so the upper and the lower have to come from the context of the question, Tricia, somehow. So in this case, the way I figured that out is I want to figure out what's the probability of this quantity being positive. So I interpret positive as greater than 0. And so for me, I visualize it on the normal curve. Here is 0. If I want everything greater than that, I want to color in everything to the right. So my lower boundary is at 0. That's my lower. My upper boundary is to infinity and beyond. So there isn't really an upper boundary, right? But we got to put something. And so you just pick a really big number. So if the middle is 0.2, what's a really big number compared to 0.2? 1,000 is gargantuan, right? And so I just picked 1,000 because it's way the heck out there. Could you have put like 10,000? Yeah. 100,000? Sure. All right, that one was sort of arbitrary. In this case, the really important one was 0. Was it 997? 9997. Oh my goodness. All right, almost a guarantee, right? So what the heck does this mean? I am recording right now, yeah. So I'll get it up on the website, hopefully this afternoon sometime. All right, so what does this mean? What does this mean? This means there is a 99.97% chance that, what does it mean if that proportion, P1 minus P2, is positive? That the sample proportion for Edison will be greater than Sunnyside. I suppose I could put even more context. This is about the percent of people that did the homework. The sample proportion of students that did their homework for Edison will be greater than Sunnyside. Because when Edison is greater than Sunnyside, that's when this P1 minus P2 is positive. And there is a 99.97% chance that we will actually get a positive value. That Edison will, in fact, be greater than Sunnyside. Okay. All right, one more analysis question, because that's pretty much all you got to be able to do. Set up, get your mean, get your standard deviation, and then go from there. Suppose Mr. Bolt and Mr. Schneider compare their samples. They get P1 minus P2 to be negative. This means that a higher proportion of Sunnyside students did their homework compared to Edison students in our sample. What would we conclude from these samples? So if this were to happen, we have to think about it for a little bit. What does that mean? The sentence that I just wrote said, wait a minute, there's a 99.97% chance that Edison's will be greater than Sunnyside, based off of all our calculations. The chances of this result actually being negative, that Sunnyside was actually bigger than Edison in the sample, was next to impossible, based on our calculations. So if our actual observation is that Sunnyside was greater than Edison, well, we've got to rethink all our calculations. This means that the assumed population parameters beforehand were probably wrong. Okay? Let me put that into a sentence here that might help you see that. If our population parameters were correct, the chances of P1 hat minus P2 hat to be negative were extremely low and shouldn't happen. All right? The chances of Sunnyside being higher than Edison was almost non-existent in this scenario. So if the sample that we took shows that to happen, we have to question the original parameters of this question. So if this did happen in our sample, we have reason to believe, my bad, spacing, it's hard. Our population parameters were wrong. All right, there was a 99.97% chance that Edison's numbers were greater than Sunnyside's. So when we actually take the sample, if that's not the case, then we're gonna have to doubt those original population numbers. That 70% and that 50% from the beginning, we're gonna doubt those. Because the result we saw, P1 hat minus P2 hat being negative, should not have happened. But again, that was a suppose. Suppose that's what we saw. Then we would have reason to believe our population parameters were wrong. All right, recap before I send you off to practice this, all right? Because I'm pretty much done here. You've got to be able to check the shape, center, and spread of population 1. Then you've got to be able to check the shape, the center, and the spread of population 2. Once you do that, you can then think about combining those two populations. You've got the shape. The center, you can simply subtract P1 minus P2. And then the calculation for standard deviation is a bit tedious. You've got to find the variance, square the standard deviations to find the variance, add the variances, then you can square root to go back to the standard deviation. All right, that's your pretty brutal calculation for today. Once you have that, you now have a new normal model with a mean and standard deviation. So now then I can ask you probability questions for that combination, like this. It'll be a normal CDF. From the context, you do have to figure out the lower and the upper, and then interpret your answer. Hopefully that's not too bad. And hopefully you're like, oh, I do kind of remember doing that last semester, Bolt. Maybe. A little bit. All right. So we'll see. I'm going to send you this here GeoGebra link. Not Geo. Why do I used GeoGebra so much before now, and now I'm using Desmos. They're basically the same program. But I'm using Desmos now. Got to learn new things. Click on that, ladies and gents.